So my name is Saad Ali. I'm a software engineer at Google. I started on the Google Kubernetes team pretty early on, way back in December of 2014 when the team was pretty small, and it was before Kubernetes 1.0. I was a young engineer. There was a lot that I didn't know, and I'm not very smart, so I didn't really pick up on the Kubernetes ideas very quickly. For me, when I start to learn things, learning all the little things, how to do them, doesn't really work for me. What I need to do is try to understand why things work the way that they do, and that kind of sticks better in my head. And so I recognized some patterns that I've seen in Kubernetes that kind of help me understand the API and understand how Kubernetes works a lot better, at least for me. So I was hoping to share some of that with you today. For a lot of you, this may be material that you're already familiar with. But it's interesting just to call it out and recognize it and see it apply to future patterns. So what's in it for me? A deeper understanding of Kubernetes. Again, an important tool for learning is to understand the problem, the why, not just the what. If you get a large collection of what's, it's impossible to memorize everything, but if you understand the fundamentals of how things work, then it's easy to extrapolate and come up with your own understanding of how things should work, and that can lead you pretty far. What is Kubernetes? I think most people in this room probably already are familiar with that. By a show of hands, how many of you know what Kubernetes is? All right, good. How many of you have deployed a pod in production? All right, good. Well, just to recap and set the stage, I want to introduce what the problem space was that we were working with. Before Kubernetes was a thing, before Docker was a thing, folks were running distributed systems largely either on bare metal or in virtual machines. When containerization started to take off, it provided a way to be able to do consistent, repeatable, reliable deployments. You could have multiple applications coexist on the same machines and not have to worry about their dependencies colliding, for example. But containers were great, but you had to figure out how to actually deploy those containers at scale, and that's where Kubernetes came in. You didn't want to get into the business of actually writing your own system to be able to SSH into every machine and start a Docker container and write some monitoring service to monitor those containers. So Kubernetes really filled that niche well. Let's take a step back and talk about the very fundamental operations in Kubernetes. So how do you deploy a workload on Kubernetes? When I first came to Kubernetes, my understanding was kind of based on my previous knowledge, which was very much there is two entities, and there's a master and a slave, and the master tells the slave what to do. In this case, you have a user. A user wants to start a container. The model in my head traditionally would be they pick a machine and they say start this container on that machine. Of course, there's a set of problems with this approach. What happens if that container crashes? So this was the model that I was talking about before Kubernetes, where if you were SSHing into machines and starting your container, that container died or that node died, or for some reason that SSH connection dropped for a second and you weren't able to actually get that container started, what happens? You have to write a lot of custom recovery logic to monitor your service, monitor your application, and then you have to take recovery action. So if the service isn't behaving as you expect it to, you'd have to write custom logic to recover it. And so you're writing a lot of custom logic just to keep your application running. So this is where the first principle of Kubernetes comes in, and that is that the Kubernetes API is declarative rather than imperative. So in Kubernetes, you do not tell the system, start this container on this machine. Instead, you define the desired state. You say that I want to have a container running. Please make it so. So this is the difference between, for example, a pilot flying an airplane themselves versus setting an autopilot. When they're flying the plane themselves, they're constantly providing input, they're monitoring, they're trying to figure out where it should go. When they set an autopilot, the computer takes over and there's control systems that monitor and make sure that whatever the requested altitude is maintained. So you can think of the declarative API in a similar way. It's a way to say, this is what I want my intended state to look like, please make it so. And the difference is basically this is what Kubernetes is all about. Instead of having to provide a set of instructions and monitor things and then provide more instructions, you just say, make this happen. And that's the basis of Kubernetes. So let's get a little bit more concrete. The way that you create or do anything in the Kubernetes API is that you create an API object that is persisted on the Kube API server until you delete it. And all the components within Kubernetes will work in parallel to drive towards that state. So for example, when you want to get a workload running, you can use one of the basic primitives, the replica set, which many of you are probably familiar with, that says, I want to create a container, maybe an Nginx container, and I want one replica of that running across my system. Once that object is created, the system kind of figures out what needs to be done next and schedules the workload appropriately and gets it started. You're pretty much hands-off at that point. You don't need to go in and monitor the status of your workloads at all. Kubernetes will take care of it. And what is the benefit of this approach, this declarative approach? And the primary benefit is automatic recovery. Meaning if something happens to your application, if the application crashes, if the node crashes, Kubernetes will automatically take care of recovering that application for you, moving it around. So now let's revisit this or deep dive into this a little bit more. So what actually happens when you create a replica object on the Kubernetes API server? You say, I want a pod of a certain definition created on my cluster. How does the node figure out that it's supposed to be running this? Does the master tell it? Like, how does all of that work? My natural inclination would be that since you have a master, the master would figure out which node this particular workload would be scheduled on. And then it would just call out to that node to say, please start this container. And that's, if you look at a lot of traditional server client setups, this is the way that things work. You issue a network RPC, and the caller tells the server or the client what to do. The client tells the server what to do, and the server will execute that action and return either a success or a failure. So in this case, that was an option. The Kubernetes master API server could have been built in a way where it could call out to the node that it selected and say, please start a container. But there were the same set of problems that we discussed with a user manually telling a specific machine to start a container apply here as well, right? Think about what happens if a container dies, or if the node itself dies, or if the node is unable to accept that command at the moment that the master decided to send it that command. How would it recover from that? If we had an imperative API where the master was calling into the nodes to tell the nodes what to do, that means the master would have to be infinitely more complicated. The master would have to begin to store the state of every single component that it was responsible for. It would have to play catch up every time it discovered that these components weren't doing what they were expected to. So first it's figure out what they're supposed to do, understand that they're not doing what they're supposed to do, and then issue follow-up commands to fix that. So that means that every time Kubernetes is extended, every time a new component is added, this master control plane grows larger and larger and larger. And if Kubernetes had been built that way, honestly, I don't think it would have been very successful. It would have made the master very complex, brittle, difficult to extend. So this is where the second principle of Kubernetes comes in, and that is that the Kubernetes control plane is transparent and that there are no hidden internal APIs. This is extremely powerful for multiple reasons. What does it mean actually? What it means is that that same declarative API that we expose to the end users is the same API that all the internal Kubernetes components use to interact with each other. And so the benefits of that declarative API then apply to the components themselves. So whereas before, if we had followed the model that I was suggesting earlier where the master would call out to individual nodes to tell them what to do, if we follow that model, you would imagine a master would have to provide an exact set of instructions to say the node should do something. The node would execute those instructions and return a response. And then the master would have to have some sort of way to monitor those nodes and then issue commands to rectify anything that went wrong. Instead, what happens is that the master basically defines a desired state for a node to be in. Once the master figures out that a workload should be scheduled on a particular node, it will essentially state that in the API server. So the master just talks to the API server. And then all the components, including the node, work independently to drive themselves towards that state. So let's take a look at what that looks like more concretely. So the way to think about it is that the Kubernetes API server is the center of everything in the Kubernetes world. This is what you interact with, but it's also what every other component in Kubernetes interacts with. So basically what happens is that all the nodes, when they first come up, will monitor the Kubernetes API server to try and figure out what are they supposed to be doing. So instead of having the decision being centralized and being sent out, every component is responsible for its own health and keeping itself running. So whenever a component comes up, it goes to the API server to figure out what it should be doing. The benefits of this approach are that if a component crashes for some reason and it comes back up, it can easily recover just by looking at the API server and figuring out what it's supposed to be doing. This pattern is called level triggered instead of edge triggered. You can imagine a system that's based on events to be edge triggered, where you issue an event and then the system will do something, but if the system is down for some reason and didn't receive that event, you're responsible for sending that event again. Versus level triggered, meaning you set this state, and then if there's a momentary issue with any of the system's components, whenever the system comes back up, it can just look at what the current state of the signal is and be able to operate off of that. So this is the way that the Kubernetes API works again, and let's just walk through that. So you as an end user operate against the same Kubernetes API. You declare that you want a workload running. You define what that should look like, and then you're hands off. Now there's an object that exists in the API server that defines what should be happening, and all the other components are watching the Kubernetes API server going, oh, something needs to happen here. I need to make sure that I do something. The scheduler is just another component in Kubernetes that all it does is monitor the Kubernetes API server looking for unscheduled pods. Unscheduled pods are just API objects that are of type pod and don't have the node field filled in. So if it finds one of those, it starts executing its logic to figure out what the best placement for this particular pod is going to be. Once it makes that determination, instead of calling out to that node, it just updates the API object to say, hey, this object has now officially been scheduled to a particular node. And then the node that it gets scheduled to is also watching for pod objects, but it's filtering those pod objects to pods that match the same name as itself. So it's a very simple concept, but very powerful. And once a node recognizes that there is a pod that should be scheduled to itself, it can look locally and see if that the containers for that pod are running or not, and start the process of getting those things running. And as long as that API object exists, the node agent, the kubelet, can basically ensure that it remains in that state. So if that application crashes for some reason and the pod indicates that it should be restarted, the node, the kubelet agent, can automatically do that. So then when you decide that you don't want that workload, you simply remove the API object from the master, and then the components see that there's a difference. There's something running in the system, and that doesn't correspond to the desired state set by the user. So all the components will work to drive towards the desired state, which in this case is, please stop running this workload. It should not be running. So what are the benefits of this no hidden internal API principle? I think I talked a little bit about this already. Components that are level triggered instead of edge triggered tend to be more robust, especially for distributed systems where you have to expect that You're going to have so many components that make up your system, something is always going to be failing. And so you have to design your system for reliability and be able to tolerate failure of any one of those components. So if your system was edge triggered, it would have to be much more complicated in order to have one component constantly figure out what the state of everything should be and figure out what it should be doing instead. If you distribute that responsibility to every single component to figure out what that component itself should be doing, it makes the system more reliable, but also more extensible. And there is also no more single point of failure. So in the previous example, if the master was calling out to everything, if the master goes down, your cluster is down. With the model that Kubernetes has, with a Kubernetes API server acting as a central point, if the Kubernetes API server goes down, all the components continue to operate on whatever the last state was that they saw. And when the Kubernetes API server comes up again, they can start operating on whatever the new state is. And if any one of those components goes down, the other components can continue to function independently of that. So there's no single point of failure, and the system overall is more robust. And it also makes Kubernetes very extensible. And this is, I think, the big reason that Kubernetes has become as large as it is because it's very simple to add on to it. Because all the components within Kubernetes use the same API that you use to interact with it, you could swap out any one of these components with your own implementation. So for example, if you wanted to write your own scheduler, all you need to do is write a binary that is able to interact with the Kubernetes API server and fill in the node field of a pod object. That is what a scheduler does. It looks at pod objects, it runs some algorithm to figure out where it should be run, and it updates the API server. So you could write a custom scheduler for Kubernetes pretty easily. Of course, writing a custom scheduler is not an easy task, of course, but the idea is that Kubernetes makes it possible, and this is true for all the components that exist within the Kubernetes ecosystem. Okay, now let's talk about some of the interesting information that exists on the Kubernetes API server. We have the idea of secrets. If you have some sensitive information, you should not be putting those inside of your containers, obviously. That information should somehow be injected inside your container at runtime so that the sensitive things aren't going to be leaked along with your container. And the facility that Kubernetes provides to do this is the secret API object in Kubernetes. It's just another API object, and you can declare a secret, give it a name, and then provide a set of key value fields. Similarly, there's a way to be able to provide configuration information to your application. So for example, your application may have some set of startup parameters for a particular configuration, or whatever other configuration information you may have. And downward API is another Kubernetes API that allows you to fetch basically name, namespace, UID, pod information about the pod that this workload is running in. All of this information can be very valuable to the application itself. So how does a Kubernetes application get access to this information? We talked about the fact that this Kubernetes API is, it's the same API that's used by the internal components, which means that if you write an application that needs to use a secret, you could basically have that application call out to the Kubernetes API server to fetch that secret and use it within your application. You could also have it call out to the Kubernetes API server to fetch information about the pod that it's running in or any configuration information from the config map API objects. This is possible, but it's not necessarily the best solution because of Kubernetes principle number 3, which is meet the users where they are. What we want to do with Kubernetes is make it easy for folks that already have applications running to transition into Kubernetes. If we required folks to actually modify their application in order to work within Kubernetes, that would be a non-starter for a lot of folks. You're all probably aware of some legacy application which hasn't been touched in a very long time. It knows how to consume secrets from a volume or an environment variable, but nobody's going to go in and modify that to have a new Kubernetes API, right? So what we did was, in addition to being able to call out to the Kubernetes API server, there is the ability for you to consume secrets, config maps, and downward API objects as files within the container or as environment variables. So as part of your pod definition, you can specify, please expose to my containers this set of secrets or config map information, and Kubernetes will automatically make sure that that information is either mounted in as a file into that container or as an environment variable. And so your application doesn't have to be modified as long as it knows how to read a file or read from an environment variable. So why did we do this? And of course, the reason is to minimize the hurdles for developing applications to deploy on Kubernetes. We want to make it as seamless and easy to transition to Kubernetes as possible. Again, I keep mentioning that these are the reasons why Kubernetes has been successful. And I think one of the reasons is because it made it easy to transition some of the existing applications to Kubernetes. Okay, next up, let's talk about remote storage. This is an area that I am very familiar with. I'm the storage SIG lead. And the idea here is that containers alone are not sufficient because they are ephemeral. If you start a container and you write anything inside of that container, that file system gets basically deleted as soon as that container is terminated. If you're running any sort of stateful application, you need some way to be able to persist state beyond the life of an individual pod. And the facility that Kubernetes provides to do this are Kubernetes volume plugins. We have a number of volume plugins that allow you to plug into remote storage systems. So if you're running in a cloud environment, you could be using, for example, GCE persistent disks or Amazon EBS block volumes. You could use an NFS share. A number of different options exist. One way to be able to use them is in your pod definition to directly reference the type of volume plugin that you want. This, of course, isn't the exact YAML that you're going to use, but the idea is that inside your pod configuration file, you specify the volume that you're going to use. So in this case, I would say that I want to use a GCE persistent disk named PD1. So as soon as I define that on the API server, Kubernetes now needs to figure out how to make that volume available to the container. And how does it do that? So first up, we have our lovely scheduler that'll kick in and try to figure out where this workload should be scheduled. It realizes that node 1 has availability, so it's going to schedule pod A to node 1 simply by updating the pod configuration API to add a field that says it's been scheduled to node 1. Now there's a second component. This is the attach-detach controller. The attach-detach controller, like every other component in Kubernetes, is monitoring the Kubernetes API and acting on a set of API objects. In this case, it is looking for pods that have been scheduled to a node and are also referencing a remote volume. When it finds one of these pods, what it does is figure out if that volume is available on the node that it has been scheduled to. So for example, in this case, pod A has been scheduled to node 1, but GCE PD1 is not available on node 1. So what this attach-detach controller would do is take action to call out to the GCP backend to say, please attach GCE PD1 to node 1. There's a step that I'm skipping here, which is it now actually updates the Kubernetes API server to say that the volume has been attached. In prior code, it didn't used to do that, but with the current iteration with CSI 1.0, and which is coming out in Kubernetes 1.13, there's a new object called the volume attachment object, which represents the state of a volume attachment. And that's used to communicate back and forth, and that's through the Kubernetes API server. So once a volume is attached to the node, the kubelet basically is just operating on API objects, and it notices that there should be a pod running, and this pod is referencing a GCE persistent disk, so it will monitor the node object to figure out whether that volume has been attached to that node or not. Once it has been attached, it'll go ahead and proceed with making that volume available inside the container. So when your container starts on this machine, that remote volume is now available inside your container, and anything that you write to that directory will be persisted to that disk. If your volume dies for any reason, it gets rescheduled to a different machine. The attach-detach controller will move that volume to the other machine, and your storage is available. Anything that you wrote is persisted whenever that container comes up on any other machine. So this pattern is very powerful, and it uses a lot of what we've been talking about, but it's not something that you should be doing. You should never reference a particular type of storage directly inside your pod. And let me talk about why that is the case. The problem is that when you reference a particular type of storage inside your pod definition is no longer portable. So if I reference a GCE persistent disk directly inline in my pod definition, if I were to take that pod definition and move it to AWS or on-prem where that GCE persistent disk storage just doesn't exist, my pod is not going to be able to start running. So in order to fix this problem, we created an interface called the PVC and the PV, a persistent volume claim and a persistent volume. The purpose of these objects is to decouple the request for storage from the actual implementation of storage. So now in your pod definition, instead of referencing a GCE persistent disk, what you would reference is a claim, a persistent volume claim. And a persistent volume claim is simply another Kubernetes API object. This Kubernetes API object contains generic information about the type of storage that you want. It could include things like the capacity of the storage you want, the access mode, whether it's read-write, read-only, information like that. So it's a very generic way for you to describe the requirements that this application needs for storage. And then there is a controller that exists called the persistent volume controller that will try to match your request for storage with what storage is available. In this case, you have two options. One is that as a cluster administrator, you could create PV objects ahead of time that represent the storage that's available on your cluster. And then the persistent volume controller will bind any PVCs that it sees with an available piece of storage whenever the PVC object is created. So what this means is that if you were to transition into another environment, your pod and PVC objects, the objects that are user-facing, are now portable. So as soon as you drop it onto a new cluster, as long as there's some PV available on that machine that can fulfill your PVC, they'll get bound and you'll have persistent storage available to you. This goes a step further with the storage class, which allows automatic provisioning of storage. So if the PVs don't pre-exist and there's a storage class defined on your system, when a PVC is created, the storage class defines how to create new storage from scratch. And that storage class is specific to that cluster environment. And so as long as a storage class with the same name exists in both environments, some sort of storage will be able to be created for your workload to be able to, for you to use. And the application-specific API objects that you have remain portable across environments. And this is basically the fourth principle of Kubernetes. It's about workload portability. And I think this is the most critical piece of Kubernetes. The way that I think about it is like an operating system. If you went back before operating systems were a thing, folks were writing applications directly for specific hardware. And those applications were not portable across different machines. And operating systems basically said, don't worry about the underlying hardware that's available on this particular machine. write to this interface that I provide you, and as long as this operating system is running on one of these environments, your application will work. And that allowed application ecosystems to thrive. In the distributed systems space, we haven't really had anything equivalent for a very, very long time. Basically, everybody was writing custom applications for custom cluster implementations. And what Kubernetes has done is it's acting like an operating system for distributed systems. It basically has southward-facing APIs that it'll hook into different clusters, and it has the Kubernetes API that it exposes to end users. And as long as application developers deploy against that Kubernetes API, as long as Kubernetes exists on that cluster, their application just works. It doesn't need to be modified. It can be moved around from cluster to cluster to cluster. It basically, excuse me, it decouples distributed system application development from cluster implementation. It acts like a true abstraction layer. So in review, the 4 principles that I talked about were the Kube API server being declarative rather than imperative. I want to get some audience participation. Can someone tell me why that is important?
Self-healing.
Sorry, say that again?
Self-healing.
Self-healing, yes.
Roll back.
Able to roll back.
Extensible.
Extensible. So no hidden internal APIs.
Immutable.
Immutable.
Yeah. I can send it the same exact structure and templates in a different namespace, and I know it will always be the same.
That is an excellent point, so I should include that in the presentation as well. His point was that it's immutable regardless of the great thing about this kind of configuration that Kubernetes has is you can actually check it into source code, and it's repeatable. You can deploy, you know how to create an application from scratch. As long as you deploy this set of YAML files on any cluster that has Kubernetes, you're going to have your application running. So it is immutable. Let's talk about meeting the users where they are. Why is that important? Ease of adoption, yes. And then finally, workload portability. Why does that matter?
Cloud agnostic.
Cloud agnostic, cluster agnostic. That's right. It's a portability layer. It's an abstraction layer. There is a principle of being able to a separation of concerns, basically. If you design your system with a separation of concerns and you isolate different components with very distinct, basically, contracts between them, it becomes much more easier to test, much easier to upgrade and maintain overall. And Kubernetes basically acts as a separation of concern abstraction layer that says, don't worry about anything below this layer, I'll take care of that. You worry about the application layer. That is all that I have. If you have any questions, please, yes?
So during the keynote and with the lightning talks, they talked about custom resource definitions, CRD, and that there's a movement to take everything and move it that direction. Is the idea of a CRD isomorphic to the existence of, like a pod object on the API? In other words, if it exists on the API, it is a CRD, and that is what it means to be.
Good question. So the question is about CRDs, custom resource definitions, and how they relate to pod objects or any other API object that currently exists as a built-in type in the Kubernetes API. So for those of you who aren't familiar with what CRDs are a way to be able to write your own custom Kubernetes API object type. So for example, you are probably familiar with the Node API object or the Pod API object. But if you wanted to create your own API object, a CRD allows you a very easy way to do that. You define a new CRD of your type, and you define the schema for what that looks like. And then you can create your own objects. You could call it, foo or blah or whatever you want against the Kubernetes API server. And then you could write your own custom controllers that use those CRs and CRDs to basically extend Kubernetes. And so the question is how they relate to these built-in types. I like to repeat what Tim Hawkins said about this, which is that if we had CRDs on day 0 for Kubernetes, there would be no built-in types. The idea is that the Kubernetes API machinery should be distilled down such that it could be used as just API machinery for any project, not just Kubernetes. So we're starting to see it be used for things like Istio and other higher level projects. And there should be no built-in API types, meaning that if we started from day 0, pods, nodes, everything else would also be a CRD.
And then, from that perspective, is a persistent volume like a pod in that it dials in and talks to that object?
Yes, well, persistent volume claim is similar to a pod. When we first came up with the persistent volume claim and PV, it was kind of modeled after a pod and a node, where a node represents the cluster resource that's available, and a pod represents kind of a request for using that resource. So a PV represents the resource, the storage resource that's available on that cluster, and a PVC represents a user's desire to use that resource, and they kind of bind together. So a weakness of what system? I missed the first part.
Declarative.
A declarative system.
You need like strong consistency guarantees. Then that's kind of hard.
Strong consistency guarantees in what regard?
That your app, you have a guarantee that after a certain period, after the modification request has gone, that the pod is there.
Right. Yes. So the comment is that one of the drawbacks of a declarative system is that you can't offer consistency guarantees, and this is absolutely true, which is why Kubernetes is an eventually consistent system. It will try essentially forever to drive towards the state that you specify. And this works well for a lot of the use cases that we have in Kubernetes, especially in terms of getting workloads running and keeping them running. But it is definitely a challenge when we have patterns that don't necessarily fit into this model well. So for example, on the storage side of things, we're looking at the ability to take a snapshot. A snapshot is a very point-in-time, time-constrained operation. And when you have something like that, it is a little bit difficult to model in a declarative API. If you're interested, you can come to the storage SIG and we can talk about how we're trying to make that work. There are issues with it, but we have been able to get something working. Any other questions? All right, thank you very much.